Hi everyone. Just wanted to record a quick video here. Unfortunately, I'm not able to be in today, but what this is meant to kind of replicate is the notes we would have finished in class today. So follow along and please let me know if you have any questions. I'm going to quickly walk through kind of a refresher of what we did last class on vectors. Then I'm going to finish up these notes with a few examples, and then you can get to your work that I've posted out on Schoology. So we started talking about vectors in last class. Vector quantities are this new type of number that we're dealing with, in that they have both magnitude, right, quantity, and direction. This idea of a directed quantity is really what's new here. We've been dealing up until this point with scalar quantities. They involve magnitude but no direction. Now, this idea of a directed line segment is really the visual representation of the way we see vectors, mathematically, right? They kind of look like rays, these arrows pointed from a tail to a head. The magnitude we've discussed is the length of that directed line segment, and it is written using these double bars. And just as a quick aside here, vectors will show up in text as bold, but if we're not, typing here, we want to make sure we put those arrows above our vectors. So we worked through some examples, right? The big idea here is that once we're on the rectangular plane, we can use a lot of the formulas we've already used to make sense of these vectors. Here we have our magnitude formula here, from 2 points. But if you look closely here, that should seem very similar to our distance formula, right? Or just a kind of different type of a Pythagorean theorem. So we also showed that vectors can, if they're to be shown to be equal, we need to show that they're both the same magnitude and the direction. And when we show direction, we want to use slope. The thing to remember there is that we always need to use the terminal point as x2, y2, and the initial point as x1, y1. The reason that matters is because with vectors, direction matters. We then started talking about operations with vectors, and this is what you guys will spend a lot of your time practicing today. Scalar multiplication is when we multiply a vector. And really what we're doing is we're making that vector larger or smaller by the factor that we're multiplying it. If we multiply a number by a vector by a negative scalar, the direction will change and go in the exact opposite direction. Adding two vectors, you can see here when we add two vectors, we put the so here we have, let me make sense of this. We have vector A being added to vector B. So what we do is we put the tail of vector B on the head of vector A, and the resultant vector is the sum of those two vectors. If we wanted to subtract, we do the same thing. However, we put the head of vector B on the head of vector A, and as a result, we move in the opposite direction. So you can see here, this is vector B, and this is the opposite of vector B. They have the same magnitude. They really just are going in the opposite direction. Now that can be a little confusing, having to use these images. So the big idea that we use here are these unit vectors that have a magnitude of 1. And we use two vectors quite a bit, I and j unit vectors. The easiest way to think about these are the unit vectors along the axes, where I represents the horizontal component of a vector, and j represents the vertical component of a vector. Because vectors can be kind of moved around, We generally use this on our coordinate plane where the tail of the vector will be placed at the origin. And then we can use the a and b values interchangeably with our x and y coordinates. We can also rewrite these a and b values if we're given 2 points. And really what the key idea, it's the horizontal displacement. How far have I moved horizontally? And that's our a value. And the b value, right, would be multiplied by j. That is the vertical component of these vectors. Right, our a value is the difference in x. Our b value is the difference in y. And those are associated with those unit vectors. We looked at the vector represented here as negative 3i and 4j. Again, using those basically as coordinates, right? What we ended up plotting here, this coordinate is negative 3. That's our horizontal component, and 4, our vertical component. So that's basically where we paused. There's just a few problems here that I want to walk through with you guys, and then I'll let you get to work. We have 2 vectors here, v and w, and they want us to perform some operations. So if I want to add these 2 vectors together, all I need to do is add their horizontal and vertical components. So 5 plus 6 will get us to 11i. And then 4j minus 9j is going to get us to negative 5j. It is as simple as it seems. When I subtract, really my w vector will have the opposite signs. So instead of adding, it's really going to be 5 plus negative 6 or negative I. And then 4 minus negative 9, or in other words, positive 13j. Now, when I subtract w minus vector v, it's going to go in the opposite direction. So 6 minus 5 will get us to I. And then negative 9 minus 4 will get us to negative 13i. Excuse me, j. Now, one thing you should notice here when we subtract in the opposite direction, our vectors have the same magnitude but have opposite direction. This should make some sense, right? It's the same as what we saw, like regular old subtraction, right? 5 minus 3 is 2. 3 minus 5 is negative 2. All right, 6 times the vector v, we are just going to simply distribute that 6. So when we multiply, we're going to multiply each component, and we'd be left with 30i plus 24j. On number 10, we want to take vector w and multiply it by negative 3. Again, we're just distributing here. Negative 18i plus 27j. Finally here, the unit vector of v. Now, vector v looks like this. It's 5i plus 4j. And if I want to make this a unit vector, I'm going to divide this by the magnitude of itself, right? The magnitude of vector v. Now, the magnitude here is really just the Pythagorean theorem. It's going to be the square root of 5 squared, which is 25, and 16, which is 4 squared. So the square root of 41. Now, we don't love having those radicals in the denominator, so we can write this as 5 root 41i. Oh, sorry, that's a j. Plus 4 root 41j all over 41. Now that looks a little bit messy, but what we've done is we've taken the vector itself and divided it by its own magnitude. That way, that magnitude has become 1 when we divide it by that square root of 41. So here, there's a couple application problems. On number 12, they tell us that the wind is blowing at 20 miles per hour in the direction 30 degrees west of north. And we want to express this velocity as a vector in terms of I and j. So what I've done here is I've drawn a diagram. Right, we have 30 degrees west of north represents this angle in here. And we know that the magnitude is 20 miles per hour. Now what we've created is a 30, 60, 90 triangle, which allows us to fill in that the I component, right, the horizontal component is, it would be 10 units, but because we're in the second quadrant, we end up with a negative 10 there. And our vertical component, associated with j, gets us to 10 root 3. So if we wanted to write this using I and j, we can write the vector, as you see here, negative 10I plus 10 root 3j. All right, let's take a look at this last problem. So first, let's just make sense of what's going on, and then I'll kind of walk you through some ways to approach this. So we have two forces, force 1 and force 2, of magnitude 10 and 30 newtons respectively, acting on an object. The direction of force 1 is 20 degrees east of north, and the direction of force 2 is 65 degrees east of north. What they want us to do is find the magnitude and the direction of the resultant force to the nearest hundredth. Now, just to visualize this here, this would be our force 1. And then this would be force 2. And the way I've set them up is as the sum of two of these vectors, so that the resultant force, really what we're trying to find, is going to be the magnitude and direction of F1 plus F2. Here in purple we have force 2. Now I find a diagram like this helpful to figure out what's going on, helpful to make sure that your answer makes sense. But if I'm adding vectors, I really prefer those i's and j's that we saw earlier. So what I did is I said, well, let's figure out each of these forces independently in terms of I and j. Well, force 1 has a magnitude of 10, and it occurs at a 70-degree angle. Remember that when we talk about bearing, right, that 20 degrees is represented here, but the complement, right, that 70-degree angle is really what we're going to use when we're dealing with our trig. Similarly, force 2 has a magnitude of 30, and that's at a angle of 65 degrees north of east. So we're going to use the complement angle there, that 25 degrees. And what that allows us to do is use our right triangle trig here. So our x component on force 1 will be 10 times cosine of 70, and our y component would be 10 times sine 70. Similarly, down here on force 2, we'll have 30 times cosine of 25 for force 1, or excuse me, for our horizontal component, our x component, and our vertical component will be 30 sine 25. Make sure you're in the correct mode with our calculator. I know we've been dealing mostly with radians. We want to make sure we're in degrees here. So what we're going to do with those pieces of information is we're going to add them together, right? You can see here some arithmetic. We can see force 1 in terms of I and j was 10 cosine 70i plus 10 sine 70j, and force 2, 30 cosine 25i plus 30 sine 25j. Well, the resultant force is just going to be the sum, right? So I add the horizontal and vertical components together, and as a result, with some fancy math here, we end up with 30.61i plus 22, I didn't round that to the 100th, 0.08j. Now that resultant force becomes a little bit easier to work with now that I have the x and y components. I can find the magnitude basically by using the distance formula or the Pythagorean theorem. You can see that in red. I've squared and summed those two quantities for a resultant force of 37.74 newtons. And then I can use tangent to figure out the angle. Now, when I'm using my inverse tangent here, I find the angle to be 35.8 degrees. That is the reference angle, the direction angle. If we want to list this in bearings, we have to take 90 minus that angle to find that our true bearing of that resultant force. Guys, you can check in on Schoology. There's some extra work, practice, some homework, and some keys available that I'll have more details for you on Schoology. Please let me know if you have any questions.